Hello, this is Jack Jackson. In this video, we're going to look at a somewhat counterintuitive probability problem inspired by an old television show, actually that's now been modernized, but it was called the Let's Make a Deal, and the host was Monty Hall. And then this problem has become called the Monty Hall Program. So in the original game series, Let's Make a Deal, the host was Monty Hall. And the contestants often played a game where they were to choose one of three doors, or maybe they were curtains sometimes. And behind two of the doors was some kind of dud prize, let's say maybe like a goat or something like that. And behind one of the doors was a great prize, like maybe a new car. So after picking one of the doors, and before the prize was revealed, Monty, who knew where the good prize was, would open an unchosen door and show the dud prize. And then he would allow the contestant to either keep their original choice of door or change the remaining unopened door or curtain. And so the question is, should they change or should they stay, or does it not make any difference? So what is the probability of getting the good prize if they do not change? What's the probability of getting the good prize if they do change? Should they switch or should they stay with their original choice, or does it not matter? Well, it turns out that this is a somewhat counterintuitive problem, which even stumped some fairly good mathematicians when it was first posed. In fact, someone wrote an article about this, and a bunch of mathematicians wrote in saying the person who wrote the article was incorrect, when in fact she was correct. So actually, maybe before you go on, maybe you should try to consider this yourself and see what you think it is before we proceed. So press pause and think about it now. Well, one argument goes like this. Since there are two doors left, with one containing the good prize and the other not containing good prize, then the probability is 50% whether or not the contestant changes. So it doesn't make any difference if they change or not. They just got a 50% chance either way. Well, it turns out this seemingly reasonable argument turns out to be false. This is not true. So the correct reasoning is that if your original door has a 1/3 probability of having the good prize on your initial guess. And this is still true because since Monty knows where there's the bad prize among the other two curtains, showing you this adds no real information to you. Since the other door is the only one remaining, it has a 2/3 probability of containing the good prize. The contestant can double her probability of getting a good prize by switching to the other door. Now, it seems a little strange, perhaps, but this is actually true. And the following website has a simulation we can run of the problem. And, well, let's just go to it here. So here's the website. And if we hit play,
game show. Behind one door is a brand new car. Behind the other two doors are goats. Pick a door.
Okay, so we get to pick a door. I'm going to pick 3.
Behind door number 2 is a goat. If you want, you can switch to door number 1.
So should I switch to 1 or
Stay?
stay?
Or switch.
Well, it's better to switch. So I'm going to switch here. And this time I got the car. Of course, I could have gotten the goat. There's still a 1/3% chance, or 1/3 chance that I wouldn't get it. But look over here. They have statistics. This has been played a lot of times, the simulation. So this has been played 441,466 games. And the players who stayed won 34% of the time, and the players who switched won 66% of the time. So that agrees with my my analysis here. Okay, so let's investigate this maybe a little bit further. So the fact that Monty knows which curtain hides the good prize means that he never removes it. And while this curtain or this door starts out containing the good prize, Monty increases the probability to 2/3 by always removing a dud prize possibility. So the tree that we have here shows all the possibilities. So let's look what happens. At first, there's a 1/3 possibility that the person choosing at random will choose A, B, or C. Let's say that C is the one that actually has the car in it and the other two have a goat. So the person choosing has a 1/3 possibility of choosing the goat on door A, or the door B, or door C. If they choose the door C, well, let's do one of these first. So if he chooses door A, what's going to happen? Well, Monty is going to open door B. So now he's left with a choice, keep A or change to C. So if he keeps the door, he's going to end up choosing a goat. And if he changes the door, he's going to end up choosing the car. Okay? Now, if on the other hand, if he chooses B, it's the same thing as choosing A, basically, because what will happen if he chooses B, Monty's going to open door A, and then he's got a choice between staying with B or going to C. If he switches, he's going to get the car. If he stays, he's going to get the goat. Now, what happens if the person actually chooses the car to begin with? Well, it doesn't really matter, but Monty will open either A or B. It doesn't matter which one. And if he changes, he'll get the goat. And if he keeps the door, he'll choose the car. So notice there are an equal number of goats, and there are equal number of possibilities at the end that lead to the car, the three, okay? And there are equal numbers that lead to the goat at the end. But they're not equally distributed between change door and keep door possibilities. If we look at the change door possibilities, one is a car, here's a car, and then this one's a goat. So 2 chances for a car and 1 for the goat if they switch doors. If they keep the door, only 1 possibility leads to the car, whereas 2 lead to a goat. And so you can see there, hopefully, that it does turn out to be 1/3 chance of getting the car if he stays, and if he changes doors, then he's got a 2/3 chance of getting the car. So it's a better chance to get the car if he changes. Kind of an interesting problem. We can use the probability tree to analyze it, but it's an example of something that's counterintuitive. And occasionally you get to problems that are a bit counterintuitive with probability things, and this is a good example of that.